For the last topic, we're going to talk about continuity, which is something that we've already encountered in passing. And briefly, continuity means that there are no jumps in the graph of a function at a certain value x is equal to a. So more formally, we have the following definition. A function f of x is continuous at an interior point x is a of the domain if the following holds: the limit of x going to a of f of x is equal to the function value f is a. So what is the domain? The domain here is all values x for which f of x is defined, and an interior point is the points other than the boundary, so not the boundary of the domain. So intuitively speaking, that means that the graph of x near x is a should not have any jumps. You should be able to trace it without lifting your pencil. So let's see a couple of examples. First off, we'll look at f of x equal to x squared minus x minus 3 divided by x minus 2, and we ask ourselves, is this continuous at x is equal to 2? And here you don't have to calculate anything. You can immediately decide that no, this is not continuous. And why not? Well, since x is equal to 2 is not part of the domain of the function. So it's a value for which the denominator becomes 0, so the function is not defined there. For the second, let's change the function slightly so that f of x is x squared minus x minus 2 divided by x minus 2, and that's the case when x is different from 2 and is equal to 1 when x is equal to 2. And so here we ask ourselves again, is it continuous at x is equal to 2? So now it's part of the domain we have to calculate, so we calculate the limit of f of x. That's the limit of x squared minus x minus 2 divided by x minus 2. I can factor that out. X minus 2 x plus 1 divided by x minus 2. I get a nice cancellation, and I get that my limit becomes 3. And in particular, this is not equal to f of 2, which is 1 by virtue of this prescription. So here as well, the function is not continuous at x is 2. So continuity is defined in terms of limits. We have left and right limits, and it won't surprise you that we also have left and right continuity. So here we say that a function f of x is right or left continuous at x is equal to a if, for right continuous, if the limit for x going to a from the right hand side of f of x is equal to f of a, and for left continuous you have to go to a from the left side. So right is a plus and left is a minus. And here a has to be part of the domain. But the boundary is okay. So let's look at an example of that. So for this example, we're going to consider the Heaviside function. This is a function that comes up quite a lot in signal processing, and it's given by it's the constant value 1 for x equal to 0 or positive, and it's 0 when x is strictly negative. So if we draw it, it's negative here, and then it makes a jump at x is equal to 0, and there it becomes 1. So let's see if that function is left or right or continuous at 0. So first of all, we see from this jump it's not going to be continuous, but let's calculate that. So let's calculate the limit for 0 going to x going to 0 minus. So that's the limit of the constant value 0, because x is negative, and that's 0. And if we go to 0 from the positive side, the right limit, we get that this is 1. And in particular, we see that these two values are not equal, so it's not continuous for sure. But we also see that the right limit is equal to the function value h0, so we can conclude that it's not continuous, but it is right continuous. And in particular, it's also not left continuous. And putting these two concepts together, now we can talk about continuity on an interval. So again, we want to say something about a function f is continuous on an interval AB if, and now three conditions have to be satisfied: f continuous at every x in the interior AB, and then secondly f of x right continuous in A, and f of x left continuous in B. And intuitively, what continuity over an interval means is that the function doesn't have any jumps in the interval. So this is our A and our B, and we have a nice function like this, and then possibly outside of the interval it can have a jump or other weird things, but inside the interval it has to be continuous. So very quick example. So let's take f of x equal to 1 minus square root of 1 minus x squared, and the interval -1, 1. So you can check this quite easily, that if you take the limit of x going to c with c in the interval in the interior, minus 1, 1, then you get this for the function, and that's 1 minus square root of 1 minus c squared, which is also our function value. So this here you can do with the limit laws. And then for the two other conditions, it's pretty much the same thing. So going to minus 1 from the negative side is one, and here you can just plug in the values. 1 minus squared is 1, so that's also equal to f of minus 1. And then the third one, it's exactly the same, so I'll let you check this. And so we see that our three conditions are satisfied, and so we conclude that yes, the function is continuous on this interval. Now, we have a couple of properties that allow you to make more continuous functions from functions that are already continuous. So let's start with a theorem. So here we suppose that f of x and g of x are continuous, and c is a constant. Then we have 5 classes of new functions that we can make, and they're all continuous. F plus g, f minus g, c times f, f times g, and f divided by g. These will all be continuous. So and here I should say continuous at x equal to a, and then I can conclude that these are also continuous at x is a. And of course, for the division here, you have to have that this is only defined if g of a not equal to 0. Otherwise, you divide by 0. And there's an important corollary or consequence of this theorem, which says that, first of all, every polynomial is continuous for all values of x in a set of real numbers. And secondly, a rational function, so a quotient of two polynomials, px over qx, is continuous on its domain, i.e. the points x such that q of x is different from 0. And then last, there's a wide variety of functions that you already know that are continuous, and I'll just give them without motivating other than looking at the graph. So known functions, so all these functions are continuous on their domain. This is important. You have to check the domain. So first of all, polynomials. Secondly, the rational functions. Third, the trigonometric functions and their inverses. 4, the end root functions, so the square root, the cubic root, and so on, and the logarithm and the exponential. So here again, the devil is in the details. You have to check what the domain is because, well, they're continuous on their domain. And then to finish up, a couple of theorems that allow you to say something about continuity of compositions of functions. So here we'll start again with a theorem. And you'll see that this is quite an intuitive theorem, and in fact we've already used this in passing a couple of times. So here we assume that if f is continuous, and we have another function g of x for which the limit exists. So limit of g of x as x goes to a is a certain value b. Then we decide that, or we have that the limit of the composition f of g of x as x goes to a is f of b, whatever that limit was, and that's also equal to f of limit of g of x, x going to b. So if f is continuous, you can swap the limit and the application of f. So let's look at an example. So here we want to calculate the limits as x goes to 2 of sine of 2 minus x 4 minus x squared pi. And so we see that the outer function, that's our sine, and then the inner function, so the outer function is f, that's sine, and the inner function, the g, that's whatever we have here. And so in particular, we have to check that f is continuous, so f of x, sine of x is continuous. And actually here we can be a bit more specific, so here we only need continuity at x is equal to b. So it doesn't have to be continuous everywhere, just at that value. For sine of x, it's continuous everywhere, so it's definitely going to be continuous at whatever that b is. So here we're in luck. And then secondly, we have to find that b, so the limit of x going to 2, 2 minus x, 4 minus x squared pi is, I can factor 2 minus x, 2 plus x pi. These two drop out, and I get that my limit is pi over 4. And so given that f is continuous, we can swap the sign and the limit. We get sine of the limit x going to 2, 2 minus x, 4 minus x squared pi. We've already computed that, that was pi over 4, so we get sine pi over 4 square root of 2 divided by 2. And then last, a corollary of the theorem that we just saw. If g is continuous at x equal to a, and f continuous at y equal to g of a, then the composition f circle g, so this symbol is denoted after, so f after g, and it's defined as follows: f after g of x, that's f of g of x. So composition f after g is continuous at x is a. So we have to check two things: g continuous at x is a, f continuous at g of a, and then we get that the composition is also continuous at x is a. So let's look at a couple of examples. So for the first example, we'll take h of x equal to sine x squared, and we're interested in where is this function continuous. So we see that it's a composition. The outer function, the f, that's again my sine. The inner function, x squared, that's my g. So we can write it as f after g of x with g of x equal to x squared and f of x equal to sine x. And now we can use what we know about these two functions. So we know that sine of x is continuous everywhere, and likewise g of x, it's polynomial, it's continuous everywhere. And from that it follows that also g of x, sine of x squared, is continuous everywhere. For the second example, we take h of x equal to ln 1 plus cosine x. So here the outer function is ln, the inner function is 1 plus cosine x. For the outer function ln x, we know that that's continuous for x positive, and for the inner function 1 plus cosine x, we know that that's continuous everywhere. So in order to compose these two functions, we know that the function is going to be continuous whenever this is positive. So now we have to look for 1 plus x, 1 plus cosine x being strictly greater than 0, or in other words, cosine x greater than minus 1. We know that cosine x is always between minus 1 and plus 1, and we know it becomes minus 1 for pi, 3 pi, and so on. So cosine x is bigger than minus 1 when x is different from pi plus 2k pi with k an integer. And so from this then follows that h of x is ln 1 plus cosine x, continuous for all x different from pi plus 2k pi with k an integer.